So in our last example here, we got the following initial value problem. Y double prime plus 4y is equal to 8e to the negative 2t, and then we have a couple initial values, y of 0 equals 4, y prime of 0 equals negative 4. So again, we're going to take the Laplace transform of both sides there. On the left, we're going to need to know L of y double prime, but we have an identity for that from the beginning of this particular lecture, and that was it's s squared L of y minus s times y of 0 minus y prime of 0. And we can fill in the numbers that we have here. So this is s squared L of y. We can't fill in anything for that yet. But s times y of 0, our y of 0 is 4, so that's minus 4s. And minus y prime of 0, y prime of 0 is negative 4, so that's plus 4. Looks like we're not going to need the Laplace transform of y prime. So I'm going to go ahead and plug this right into the differential equation. So we get s squared L of y minus 4s plus 4 plus 4 L of y. That term right there is coming from here because we took the Laplace transform of both sides. And then on the right, we have to take the Laplace transform of 8e to the negative 2t. And again, let me remind you of the Laplace transforms we did back 2 lectures ago here in the differential equations series. So in the Laplace transform lecture, you'll see that in the list of lectures over there. In the Laplace transform lecture, we figured out that the Laplace transform of e to the at is 1 over s minus a. You can check that out in the original Laplace transform lecture if you don't remember where that comes from. So that's just a couple lectures ago here on Educator.com. And so e to the negative 2t, well, for e to the negative 2t, our a is negative 2. So that's 1 over s plus a, or sorry, 1 over s plus 2. And we still have an 8 here coming along as the coefficient. So now we've really got an algebraic problem. We're trying to solve for L of y. Think of that as being the variable and solve for that. So I'm going to collect my terms that are multiplied by L of y. I see I have an s squared plus 4 times L of y minus 4s plus 4 is equal to 8 over s plus 2. And again, I'm trying to solve for L of y, so I'm going to take the minus 4s plus 4 and move it over to the other side. So that'll turn into plus 4s minus 4. And in order to put that over a common denominator, I have to multiply that by s plus 2 over s plus 2. And I'll need to expand that out, this 4s minus 4 and the s plus 2. So if I expand that out, I get 4s squared minus 4s plus 8s. So that's a plus 4s. And then minus 4 times plus 2 is minus 8. So if I combine that all together, I have a minus 8 here and a plus 8 here. So those will cancel each other out. I'll just get 4s squared plus 4s over s plus 2. And that's still equal to s squared plus 4 times L of y. And remember, we're solving for L of y, so I'm going to divide by the coefficient of L of y, s squared plus 4. So L of y is equal to 4s squared plus 4s over s squared plus 4 times s plus 2. So that's the end of that step of the algebra. The next step is, now that I know what the Laplace transform of y is in terms of s, I need to take the inverse Laplace transform. And again, I synced these examples up to the examples in the previous lecture. So this was example 5 in the previous lecture. So see example 5. in the previous lecture, which was called inverse Laplace transforms. And what we did was we started with this function of s, and we did partial fractions on it. We worked backwards, and we finally found out a function for y in terms of t, e to the negative 2t plus 3 cosine 2t minus sine of 2t. So that's really exploiting a result from the previous lecture, example 5 from the previous lecture, if you want to look it up and see where that came from. See how we did that. We worked out all the arithmetic back there, so it's all worked out, don't worry. So that's really the end of that problem. Let me show you the steps we went through to get there. We took the Laplace transform of both sides, which meant we had to figure out L of y double prime. Well, we have this identity from the beginning of lecture, which always works. S squared L of y minus sy of 0 minus y prime of 0. And now we fill in our values for y of 0 and y prime of 0, which is 4 for y of 0 and negative 4 for y prime of 0. Of course, the negative 4 turned into a positive 4 because that negative sign canceled with that negative sign, and they gave me a positive there. And then we plug that back into the differential equation, s squared L of y minus 4s plus 4. And then that 4y gave me that term right there. But then we also had this right-hand side. We had to take the Laplace transform of 8e to the negative 2t. And we recalled from the original Laplace transform lecture, not the previous one, but the one before that, where we first started talking about Laplace transforms, we figured out that the Laplace transform of e to the at is 1 over s minus a. So in this case, our a is negative 2, so we get 1 over s plus 2. And then there's also an 8 there, so we just bring that along too. And what we find here is kind of a big algebraic expression. You want to think of L of y as the variable and solve for that. Just kind of sort out all the s's and just get a nice expression for L of y in terms of s. And so that's what we're doing here. We moved the 4s, the minus 4s plus 4 over to the other side. So that's where that came from. I wanted to put it over a common denominator. So I saw an s plus 2 here. So I multiplied top and bottom here by s plus 2. And then that's a little messy. I had to expand 4s minus 4 times s plus 2. So that expanded out into 4s squared plus 4s minus 8. And when I combined that with this 8, the two 8s canceled each other out, which is why there's no constant over here. We just get the 4s squared plus 4s, still over s plus 2. In the meantime, I still have s squared plus 4 times L of y on the left. And so when I divide that across, that joins the denominator here, and we get L of y is 4s squared plus 4s over s plus 2 times s squared plus 4. And now we have to take the inverse Laplace transform, which would be another really healthy dose of algebra here, but it's exactly the example 5 in the previous lecture. So go back and check that out, work that through, and what we figured out is the inverse Laplace transform of that is exactly this, e to the negative 2t plus 3 cosine of 2t minus sine of 2t. I see that I kind of wrote that as if it were an exponent, so let me write that a little nicer down here. 3 cosine of 2t minus sine of 2t is our final answer there. So that's the end of our lecture on using Laplace transforms to solve initial value problems. And that's actually the end of this chapter on Laplace transforms. So I really appreciate you watching. My name is Will Murray. You're watching the Differential Equations lecture series here on Educator.com. Thanks for joining us.